It's our pleasure here to welcome our distinguished alumnus, Mr. Umar Amin Umar. He's going to deliver a seminar on production systems engineering to our students, and further on, he is going to give some career advice based on his distinguished career. And I will give it to my chair, Associate Professor Dr. Murat Ozdanafe, to formally welcome him. Over to you, Murat Hoca.
Qasim Hocam, thank you very much. Omer, welcome. Good to see you here again. And our students, welcome to our webinar, which is done in the context of our design week. Our prominent alumnus, Omer Amin Mustafa Omer, will deliver a webinar on production systems, queuing models, lean principles, and Six Sigma. Omer is a licensed professional engineer and the CEO of Meyer Gulf Engineering Consultants in Riyadh, with his extensive experience in mechanical engineering, manufacturing, quality assurance, and operational excellence. He has led major initiatives in aerospace and defense, including AS 9100, ISO 9001 implementation, ERP-driven production systems, and Lean Six Sigma efficiency programs. He holds a BSc in mechanical engineering and an MBA, and he is an AS 9100 lead auditor and Lean Six Sigma certified, and serves as an ABET advisory board member of our department. His work focuses on optimizing production systems and advancing quality and process improvement in engineering environments. And again, Omer, welcome. And I want to tell our students that we will have a question and answer session at the end. Enjoy the webinar. Thank you.
Thank you, professors. Pleasure is mine to join you. Please let me know if you can hear me.
Yes, we do hear you, Omer.
Okay, so welcome everybody. I believe majority of the audience will be coming from the mechanical engineering department. So, Professor, are they? Which year are they joining from? Second, third, or fourth?
Mostly are from third year at the moment.
Okay. Okay. All right. So welcome, students. Today the webinar I'm going to give you is regarding production systems engineering. It falls within the scope of mechanical engineering and industrial engineering. However, HR departments around the world find it very hard to distinguish between the two departments. So you might be hired and you will be having the responsibility of the scope of almost of an industrial engineer. The goal of this webinar is just to give you a brief introduction to the topic. And then later on, whenever you want to research yourself, or if you have further questions at the end of the presentation, I will answer those questions. So we're going to give you a brief history from the foundations of production systems to the modern operational excellence systems that are currently in place. And also, I will talk a little bit about AI, machine learning, and big data analytics, and how it is linked with production systems, not just using ChatGPT. So AI is actually much deeper than what you students are used to. Okay, brief introduction about myself, as Professor Murat and Professor Qasim have told you. I'm a alumnus of EMU. I graduated with high honors in mechanical engineering. I have an MBA from Liverpool John Moores University. I also graduated EMU with the Best Project Award. I currently specialize in machine design and materials, which within all that, as well as manufacturing. I'm a professional engineer from Texas, the US. I'm currently an engineering CEO at an engineering consultation firm called Meyer Gulf in Riyadh, Saudi Arabia. Okay, So these are some of the credentials that I hold. I'm currently a member of ASME, a member of SPE, associate member in APEGA, Saudi Council of Engineer member, AS 9100 lead auditor, and I also hold Hellerbilt Lean Six Sigma from the Technical University of Munich in Germany. Okay, so today's topic, we're going to pass through 6 major topics. So first, I'll give you an introduction and the historical evolution of production systems, how it came about, and how we reached where we are
Omar,
today.
Sorry, slightly
Let's go
louder,
ahead.
please. Slightly louder. Thank you.
Okay, hold on.
Thank you.
Is it better now? Slightly louder. Okay. So we're going to talk about a brief introduction and historical evolution of how production systems reached where we are today. And then we're going to go through some manufacturing strategies. We're using an example, and then production flow and queuing methods. And then we will proceed to quality improvement in production systems. This will cover the topic of Six Sigma, if you've heard of it. And then we will proceed to go to lean manufacturing and flow optimization. And the last thing we'll be discussing today will be something new called Industry 4.0, which is considered as quote unquote smart factories. And then we will have a question and answer session that will talk technical questions regarding the topic. And then if you have any career questions, we'll give it another 10 minutes. And then the last 10 minutes, we will discuss whatever you guys want to discuss about. Right? At the end of these slides, I have references on where all this information comes from. Okay, so let's start with the history of production systems. Production, you can say, started since the 18th century, right before the Industrial Revolution, which happened around the 1900s. So this is a picture from a carriage factory, the one the horses used to pull, Edwin Morris factory. As you can see that it wasn't really advanced, okay? So the production system before was not industrialized. You had to have skilled, we can say, artists or skilled craftsmen who have to do the products end to end. So it wasn't, the disciplines were not compartmentalized as today, as electrical engineering, mechanical engineering. So everything was more generalized and you have to hire skilled individuals. During those times, a carriage could take between several weeks to months. So a factory like this had a production of about 20 vehicles. So you can imagine a whole year passes by and they can only manufacture 20 vehicles. Nothing was standardized. The wheels, the materials, there was no supply chain systems to support manufacturing. It was very crude and very primitive. As we move on to the early automobile craft production between the 1890s to 1908, we start seeing this type of manufacturing, this type of production, as you can see in the picture, almost like somebody's garage, where the manufactured products are in the center of the room, and then you have a skilled craftsman again who will take and assemble and craft and manufacture and cut, and all the machines were around it. So it was also not very improved. However, just the slight change changed the production from 20 in a year to about 1,700. At the time, it was such a huge leap. However, as we go through this presentation, you will realize that the cost of items are directly proportional to the time it takes to produce. So the faster things get produced, the less skilled labor you need, the less electricity, the less utilities, less resources you need apart from the raw materials. So the prices go down as time reduces, the production time reduces. So Henry Ford, the founder of the Ford Motor Company, was the one who actually started to think about increasing production. Back then, in the 1908 and the 1900s, the cars and anything that was really manufactured was only for the elite, the rich, because it was very expensive to make. It took thousands of hours of very skilled labor to manufacture it. It took a lot of resources and time, and the quality was not standardized. There is no consistency across products. There's so many defects going on. So within 5 years, by the improvements of Henry Ford, the number jumped from 1,700 to 10,000, a very huge leap, almost 10 times. Okay, so it's the high cost of long assembly lines. So 12 hours per vehicle. So it takes about a day to even 1 day to make one car. Okay, so the transition point for Henry Ford and the world, because he's the one who discovered it, was in 1913. He invented something that would later be considered the standard in mass production, which is called the moving assembly line. The moving assembly line cut down workers. For example, some skilled workers will be doing a 10-step operation, let's say 50-step operation. What he did was distribute the activity and broke it down into single task activity. So there was a point in 1913 and 1920s that in Detroit, in America, the employees that were working there did not even speak English, did not understand each other. Why? It's because what was needed from them was a single task. They had to either drill something, and they had a drawing showing them how to drill it, or they had to just assemble something. So this created the moving assembly line, which cut down from like 12 hours to about 3 hours to produce. So by 1915, once this moving assembly line was established, Henry Ford could produce almost 500,000. So you can see the great leap between 10,000, 15,000 to almost half a million. By the 1920s, he had already optimized it more than needed to even up to 2 million, or even more than 2 million parts or vehicles per year. So the thing that is amazing is that the same production line 100 years later is used in all industries, regardless of the product. So all of it, whether the product is automated, whether it's a bottle of water, a laptop, a phone, or even an airplane, they all use the same principles of Henry Ford, which was discovered 100 years ago. Of course, there are more optimization that we're going to talk about now, but you can see on the picture on the right side, you have an assembly line which is actually moving at a very slow pace. The whole floor is moving at a very slow pace, which is mimicking the same production line as Henry Ford did 100 years ago. So you can see that actually Henry Ford takes credit to one of the most significant changes for our planet. You can even say that he is solely responsible for the entire industrial revolution, because after this is where everyone adopted the system. Everything started to be free. Everyone could afford a car. Anything could be produced in the thousands. Refrigerators, anything that you gentlemen take, ladies and gentlemen, takes granted for now. Back then, people didn't have it. But because of Henry Ford and the concept of the moving production line, everything became cheap and affordable and logical. So instead of something taking a whole month to produce or 2 days, it drops down to about 3 hours. So as time progressed in the 1950s and 1970s, lean manufacturing and just-in-time system was introduced by a company, Toyota Production System. The one who takes credit for inventing this is a gentleman who was an engineer there. His name is Taiichi Ohno. Okay, he implemented many principles of these just-in-time and lean manufacturing systems. So they invented just-in-time, they invented Muda, Muri, which is called the 3 M's. There's like the 7 wastes. We're going to talk about all this as we move on through the presentation. Okay. After that, in 1986, an engineer in Motorola company, even though Motorola doesn't exist today, his name is Bill Smith, and the CEO, Bob Galvin, invented a new framework called, quote unquote, Six Sigma methodology. Okay, this was following a specific process to eliminate any defects and defective products. They follow a principle called DMAIC, which we'll talk about as we keep going. And you can see on the right side, this is actually a Motorola factory. Okay. And recently in 2011, 3 professors coined the term Industry 4.0. So what is Industry 4.0? We can imagine Industry 4.0. Why 4.0 is considered the 4th industrial revolution that is happening right now as we speak. And it's moving so fast that the 4th industrial revolution hasn't finished. We're already moving to a 5th industrial revolution, people considering it AI. So things are moving so fast right now exponentially. Okay, so what is Industry 4.0? We will talk about it. So basically, it's just the integration between the manufacturing and the IT components, the internet, the automation that is involved. Okay, so this is something that is maybe you gentlemen have seen maybe in the news. So China says that they have dark factories where robots run the show. So basically, they don't even need to turn on the lights because the process from beginning to end is all just AI monitored and just robots. So there's no one employed in the factory. Everything is controlled remotely by engineers and probably only during maintenance plan schedules is when the engineers or technicians go into the factory. So this is what I was talking about, the 5th industrial revolution. It's still not implemented everywhere, so to say. So as you can see, what we just talked about, you can see what we just talked about. The average production capacity for an automotive nowadays is almost 10 million. Of course, 10 million is not produced, but this is the capacity. They are capable of producing 10 million. As you can see, there is almost exponential curve that is going. So by 2030, we're going to see with this full 100% efficiency 5th industrial revolution AI happening, you might see production automation that is close to 100%. Okay, the efficiency, close to 100% efficiency, no time wasted. Improvements are implemented on the go. AI is monitoring, live corrections are happening. So this is, as you can see, the progression of the production capacities from 1825 to 2025, about 200 years. Okay, as you can see, 100 and almost 75 years, 175 years, it was at 2.5 million. Within just 25 years, it went 5 times. It improved 5 times more. Okay. So what do all these terms mean? The one that I talked about, okay, Muda, Muri, Six Sigma. Most of you are not familiar with this. So, and how are these speeds achieved? So how is it possible that it takes something nowadays from something that used to take 1 million, it takes 1 year, 1 month, nowadays takes a few seconds. So how are these speeds achieved? We're going to talk about next. Okay, so we will talk about manufacturing strategies, and I'm going to use a semi-trailer as an example. Okay, so this is what a semi-trailer looks like. It's part of a trailer. Most of you have probably seen it on the road. So there are many manufacturing strategies. However, today we will just talk about the 4 main ones that is seen across the industry. So on the right side, there is an image of sub-assemblies and parts and all types of components, as you can see. It's more detailed than this. This is actually just a summarized version. It shows 85 parts, but in reality, you have approximately product like this will have between 200 to 300,000 individual parts. So you can imagine how complex it is. And each individual part has its own production schedule, has its own production method, manufacturing method, and each product was designed. So it's very, very complex. Things that you people take for granted have engineers behind it who have thought about it for years. And there's huge cumulative knowledge over the years that is implemented on them. So the main key strategies of manufacturing or production are four. We're going to talk about make to stock, assemble to order, make to order, and engineer to order. Okay, we're going to use this as an example. Okay, so let's talk about make to stock. Okay, what is make to stock? Make to stock is when the parts or components of the final product, in this case, our semi-trailer, is not given by customer orders, but by an MOQ order. What is an MOQ order? It is a minimum order quantity order. So it's a minimum order quantity. What is that? Basically, there is a policy in the company for that workstation to produce an X amount of items, regardless whether there's an order or not. So they will produce, let's say, in this case, 100 sandwich panels. The sandwich panels are the ones here, okay? The ones here that are on the side of the trailer. So they have 100, they have to produce, let's say 50, they have to keep a minimum order on their station, let's say 50 sandwich panels. So as the other workstations inside the factory use up those panels, they just keep producing and meet the minimum order. This creates some sort of automatic production system based on the individuals who are working at that station. Why is this important? We will see later why make to stock is important and why we need as manufacturing engineers to maximize the make to stock orders. Okay, so the next thing is make to stock, or you can imagine order to stock. For example, the axles, the right side there, top right corner, the axles of the trailer are not manufactured in that plant. They are manufactured by specialized plants that make those things. So make to stock or order to stock, in this case, will just say that the company who is manufacturing the trailer needs to keep a minimum amount of X axles, for example, 100-ton axles, 50-ton axles, an X amount in the factory at all times. How is this done? It's done by forecasting. So based on the previous year or on the trend of the market, production engineers and the R&D engineers decide how much they should keep stock to minimize the capital expense, which is the investment needed for those parts just to sit in inventory, and what is the maximum amount that they need so that they don't have flagging in the production. They don't have delays in production. Okay. So another example is the chassis components of the trailer, which forms the main body at the bottom. So this is make to stock. Okay, so the next thing we're going to talk about is assemble to order or make to order. What is assemble to order, make to order strategy? It means that the component or sub-assembly of that item cannot be produced unless there is an actual order that has been issued for a client or from engineering, whatever it may be, in the production flow. Okay. So in this case, this affects the production capacity of the company, because the moment they get the order is the moment they start. So in this case, for example, in this case, we talked about previously make to stock. So in this case, let's say they're going to manufacture the chassis. The yellow one that you see in the screen, that's the chassis which forms the bottom bed of the trailer. So in this case, they have to manufacture this. They got an order, they need 3 or 4, client X needs 3 or 4 of these things. So if they didn't have make to stock items, but like for example, the axle, they didn't have the chassis, the one we talked about here. They didn't have this chassis already welded. What does that mean? For example, in this case, we're going back to make to stock. The axle takes about 3 to 4 months to arrive. Okay, it takes about 3 to 4 months to arrive, because in order for you to buy it, these are made by specialized companies that they do heavy engineering on these things and testing and certify them. So, and it's very, you can imagine, high-tech equipment. So nobody will manufacture it just to keep it. And usually it's based on a range of requirements. For example, how much tonnage you need, what is available, what's the dimension. So whoever needs to order these needs to keep in mind it takes 2 to 3 months to arrive. So in that case, if a client had given you an order to make a trailer today, paid, then it means if you didn't have that as make to stock or order to stock, you will need 3 months plus the remaining manufacturing time to deliver the first one. Okay? This is not acceptable in the industry. Okay, so no one will wait that long. So that's why you have make to stock. So in this case of the chassis, the wheels are ordered to stock, the lights are ordered to stock, the chassis bars are ordered to stock, the underrun device that you see at the top there, the components are made to stock. So the company keeps stock of all these components, sub-assemblies. Why? So that when an order comes, the only time that will be included in the capacity or the production time will just be the final assembly or the final manufacturing of the bed. And then in this case, we have another workstation that is doing the final assembly of the box above, and then you just join them together and ship it. So you're cutting down 3 to 4 months expected production time if you didn't have them to stock to something like 2 weeks or 1 week. So with this in mind, you can see how the manufacturing and the engineering design are linked. So if the engineers who work in R&D or working in the design department don't design things that are modular or design equipment or machines or whatever it is that is in such a way that the production can keep as a make to stock, it increases production time drastically. So instead of using non-standardized parts, it's better to use standardized parts and keep stock for them. Instead of using different sub-assembly components for different sizes, you can have a standard rib across the chassis in this case that is implemented modularly regardless of the trailer length. So regardless whether the length is 16-meter trailer or 12-meter, the ribs are going to be the same. So this is where the industrial portion and the mechanical engineering portion of the design and the production meets. So by a great design engineer will make the life of the production easy and give better customer satisfaction because of faster deliveries. While a bad design engineer might design something that is so specific or so custom that the production, regardless of how much they plan or how well they plan or how well they produce or how fast they produce, regardless, because of the design is not correct or not correct, but the design is not standardizable, it's not possible to produce it at the competitive rate in the market. So again, this is something you have to understand. When clients come to a factory, they don't just choose you. They are looking at all the factories. They look at multiple vendors, multiple suppliers, multiple factories, how fast each one produces. So if you are not correct or designing according to the industry standard, then it means that the company will suffer because no orders will come. Because company A, the one you are working in, the design is so bad, it takes 3 to 4 weeks to deliver the first one. Company B, within 2 days, they can deliver. What is the difference? It's not in production. It is in the design. Even if you have the best production engineers in both. Okay. The next thing we're going to talk about is engineering to order. Engineer to order, sorry. Engineer to order usually are special projects. Okay, so in this case, if we're taking the example of the trailer, as you can see the pictures on the right side, taken from Techno Team company and another American company, you have special trailers that are, for example, the first one is a shooting range. It's not a standard thing. And the second one is a portable clinic, portable hospital clinic. Companies had to make a lot of these ones during the Corona time. So nowadays, the clinics are also almost like a standardized part. Standardized, they can be make to stock or make to order kind of situation. Okay, so this is what we mean by engineer to order. Okay, so in the case of the standard products, for example, in the case of this standard product here, the engineer to order will be, for example, the sticker, which is called the livery, or the image that is put on the trailer to advertise. So that one cannot be pre-made. So that is made engineer to order. So the client will give you the design. You have to do the design, then you have to print it, then you have to stick it. So this is also an engineer to order kind of component. Okay? So if scheduling and planning is done correctly using something called economic order quantity principles, the industrial engineers study this a lot, and I can't get into this right now. It's because it's a whole field. Then parts produced by MTS does not affect production capacity. So what is production capacity? Production capacity is the unit rate, how much is produced per year, or per hour, or per unit time. So units per year, or units per hour. It does not affect. Anything that uses make to stock or MTS does not affect this if planned and scheduled correctly. However, MTO, okay, there's a typo there. There's MTO or ATO or ETO, which is make to order, assemble to order, or engineer to order. It affects the production capacity. It affects the speed. Okay, so it affects the production speed and affects the capacity of the whole production time. So logically, you will want to put everything as make to stock, but however, due to some certain requirement constraints, you can't actually do that. Okay. All right. So this is a typical production network. We have a macro view and we have a micro view. So the micro view is what is happening inside the factory. What is happening inside. So you have step one. There's a product, it's called a workstation. There's a workstation. Step one does something. Then there is step two. Then it goes step three, step four. But the material input is coming from another plant. For example, if your production here, you're talking about making I-beams, for example, or you're making steel sheets, the material will be coming from a foundry. So it's coming from another company. So as you can see, now, when you're dealing with production, you might have delays in production because of your vendor, the person you are buying the materials from. So now when you zoom out and you go to the macro view, you see that the vendors have a direct effect on your production time, because you need to make sure that the material arrives at the correct time, so that you can produce it with your optimized schedule. So no matter how optimized you are, you need to have some sort of agreement between yourself and your vendor. Either you will keep a minimum amount of stock, or you will speak to the vendors who have bigger warehouses and let them dedicate a specific amount of minimum order quantity in their warehouses for you. That way, you don't need to get affected by the vendors, but the same process, the same calculations that are done for each workstation can be done for the whole factory as a whole. Okay, how long does the X product, whole product, go to start to finish? Not just the component, not just the operation. the whole product. So the same thing, you can do the same network with other companies, the chain of companies that you have, because most components, as you saw in our example, you have lights, you have wheels, you have axles, you have L joints, you have things that you can't manufacture in your facility, but you can buy from outside. So you have 50, 60 vendors that are specialized in their job, and you need to keep a minimum order quantity with them so that your production doesn't get affected. So it's now you're moving on and affecting vendors. Okay, so this is the idea here, the typical production network. So each workstation, as we look at the workstation or the workspace, we have a standardized unit, how it looks. You have the order, you have the queue, you have the assembly, and you have the final finished product exit. Imagine in this case, this is a workstation for, let's say, again, this is not a make to stock, this is a make to order workstation. So you have a workstation, let's say a make to order for the whole transit. So how do you decide? You cannot have, how do you decide which client to do? So for example, the workstation that is welding the trailer chassis has a work order that is coming from Baker Hughes, another one is coming, let's say, from Aramco, another one is coming from this, another one is coming from that, based on the sales department, how the orders came in. So which one do they do first? This is what is known as queuing. So we have things like first come, first serve, first in, first out. So whatever order came first, that's what you do. So the workstation, this workstation, on, let's say, on this specific day, they will have a default priority queuing method for FIFO, of FCFS, first come, first serve. So they work automatically. The materials arrive in their station, they see which one was the earliest to arrive, and they will work on it. Or the less common one, last in, first out. So whatever came in last is what you will work on. And then there is priority queuing. For example, you have a very important client. For example, it's a very big important client you don't want to lose. So the engineering or R&D or sales department will put a priority on a specific item. So whatever items arrive in that workstation, if it's coming from that specific client, it will have a priority queue highlighted on it. Okay, and then there's other versions called service in random order. There's another queuing method called shortest processing time. For example, sometimes people use shortest processing time. So for example, you in that workstation, something arrives that will take 3 days to do, and another thing arrives that will take 10 minutes to do. So if they have the shortest processing time policy in place, then it means they will take the 10-minute job, finish it, then proceed with the three-day job. So that's how this queuing method works. Again, this queuing method is seen also in programs, okay? In queuing, in programs, in banks. So when you're in queue, the banks, they use first in, first out. So whoever came in first will be served first by the server. So it's the same methodology here, just like in a bank, for example. Okay. All right. So there is something known as Little's Law when it comes to production, especially in JIT, which is known as just-in-time production. We will talk about this also. Little's Law basically says L equals to lambda W. What is lambda W? The average number of items in the system, also known as inventory. So in the whole production system, for example, in the whole production system, from beginning till the end, how many products are in it before the last one comes out? That's known as L, or WIP, work in progress units. Okay, how many work in progress items are inside the manufacturing system or the factory in this case? Lambda is the average arrival rate of items or the throughput, or this means the production rate. Okay, so units per hour, how fast things come into input. Okay, units per hour. And lastly, of course, you have the average time that the item spends in the system. So per hour. So for example, something spends 3 to 4 days in the system. Okay. So what is this? What are all this? I'll talk about it. So here's an example, okay, of something that has a production capacity. So what are we going to talk about right now is that, for example, these are machines. Imagine the ones on the vertical column. Those are machines. Machine number 1, machine number 2, number 3, number 4, number 5. And on the right side, you have, on the top side, you have minutes. So you can see that in order to produce this specific item, it takes 25 minutes, okay? So it means the W here is 25 minutes, okay? It takes 25 minutes to produce this item. However, it does not take 25 minutes to actually produce it outside the factory. This is just the duration the item takes inside the factory. But what comes out at the end, now this is called the production capacity, is based on something called the bottleneck. What is the bottleneck? The bottleneck is the activity or the machine that uses the longest time to produce. So in this case, we have one here that takes 10 minutes in machine number 3. That is the longest time. So that is the bottleneck. So this product actually takes 10 minutes to produce. It takes 10 minutes to come out. So every 10 minutes, there's something coming out at the end of the factory. However, if you are looking and observing a single item from beginning to end, it takes 25 minutes. Okay, so that's how it's arranged. So you see that ideally the bottleneck here, machine number 3, will be utilized 100%. Meaning, what does this mean? In best case scenario, machine number 1 takes about 2.5 minutes, is almost 80% underutilized. Almost 80%. Okay, as we keep going, you'll see. So this is what utilization looks like. So machine number 1 is about 80% of the time is open. Machine number 2, about 20% of the time is free. Machine number 3 is always engaged in production. Okay, machine number 4, you can say also around 70%, and machine number 5 about 50%. So this is called utilization, and this is how the production capacity is calculated. Okay, so now that we understand production capacity, we understand the flow and the strategies and the queuing, let's proceed to the quality improvement of production systems. Okay, as we discussed in the beginning, Motorola is the one who invented this. So they follow something called the Six Sigma principles. We will talk about how it becomes 6. Why 6 Sigma? What is Sigma? What is 6? Why 6? All these questions are going to be answered. We follow a principle called the DMAIC cycle, otherwise known as the define, measure, analyze, improve, and control cycle. The first thing you're going to do, you're going to define the CTQ. CTQ means the critical to quality. So we're going to define, and back to our example of the trailer, we're going to design this, we're going to decide. So you are, as the engineering department or as the quality department, you're going to decide what is the critical to quality item, dimension or parameter. Can be weight, can be whatever it may be, can be color, but what is the critical quality? That's the first step you will do. You will define based on the data and the research, the critical to quality. In our example, we will say it is the alignment of the chassis. So the alignment of the chassis, how parallel, how the angle between each side. So in this case, you have 3 dimensions that determine that, which is like a diagonal dimension that determine that directly. So in this case, as you can see, I've highlighted, for example, the 3 dimensions. So we determine this is the critical to quality, the alignment. What are we going to measure? The 3 dimension, the one that I showed on the screen. We've decided. So in a real case scenario, you don't have one, you have hundreds. You have hundreds of parameters that need to be measured throughout. Okay. Then we move on to the next part of the DMAIC, which is analyze, improve, and control. Okay. So we're going to analyze, improve, and then control the system. How? By collecting the data we just said, and then plotting it. Okay. We will plot it using something called statistical process charts. It's a whole topic. These are just things that I mentioned. There's the X bar, R chart, the P chart, NP chart, C chart. Okay, but on average, I'm showing you here the X bar chart. Okay, what is the X bar chart? If the ones that have taken statistics, they know this. X bar is just the mean. Okay, so if the chart is showing you what is the mean, what is the average. Okay, and you should note that in real life, things follow the normal distribution. So it's very safe to use the normal and Gaussian distribution formulas. Okay, in the top example, it's showing number 1 in the first phase. You have some errors. That's why so the UCL and the LCL, those are the tolerances. What are tolerances? Okay, tolerances are just the acceptable acceptance criteria. So for example, in our case, for example, here it says the first CTQ, critical quality, is 6273.8. Maybe the higher dimension is 6275. The lower dimension is 6270. So that will be plotted. And then as each trailer is produced, the dimension is taken and recorded in a SPC chart, statistical process chart. And as the time moves on, you can see that some of the data is outside the tolerance, meaning it's non-conforming. It has to be sent back to rework, which causes delays and causes expenses. And it shows also sometimes it's at the edge, sometimes it's on the target dimension that you want. But as you assess the system and you learn to control the system, you see what is affecting these variations. Is it the worker? He's not more focused? Is it the machine? Is it out of calibration? Is it extra working hours? Maybe the items that are produced during overtime work hours, the workers are tired. So you start controlling these parameters. And you can see that then you're creating at the target dimensions. And as you keep improving the system, now you can even decrease the tolerance, and you can still be within the limit because the system is very controlled. Okay, so this is an example. This moves. So how are these things measured in a form of a parameter? It's called CPK and CPM. Okay, so the process capability. So what is the process capability? The process capability is measured with two parameters, CPK, CPM. Okay, CPK determines how well the process meets the specification. Okay, that's the items on the left, as you can see on the top side. How it meets the specification. How much of it is within the tolerance. Okay, and the value for something that is good is about 1.33. But CPM measures how close is it to the target. Okay, so the target value, if you see the bottom right corner, there is a target in the middle. You have the lower specification limit and the upper specification limit, but the average is nucleating outside. Okay, so CPM measures that. There's a whole formula for these things to measure how capable your process is. This is called the process capability, and there are industry parameters or industry level dimensions or parameter value that is accepted in industry. Okay, so this gives you we can say this gives you the acceptance criteria or the predictable dimension failure. So for example, you can predict out of 100 out of 1,000 products that you will produce, how much will fail QC, how much will be defective and will need rework, which will slow down the process, which will slow down the production system. Okay, because when you're doing rework, the machine that is supposed to be engaged in production for the actual product has to stop, and the product that has already passed has to come back and rework. So it delays substantially. So in a factory, you have hundreds of processes. So you imagine you have so much rework going on. So this parameters makes it possible so that it is capable to predict how much rework will be needed. And there are strategies on how to improve and meet the target within the upper specification limit and the lower specification limit. Okay, so now we're going to talk about what is this sigma. Sigma is the standard deviation. Okay, it's denoted by sigma. So it's the standard deviation. So the gentleman from Motorola decided that 6 standard deviation is pretty good. Okay, 6 standard deviations, if it's within the upper limit, upper and lower limit, it's pretty good. That means there is 3.4 defects in a million. So in a million products produced, you'll only have a probability of having 3.4 defective. So that's a pretty good chance. Okay, so that's how it looks like. That means being 6 sigma, when you hear the sigma, 6 sigma means that your products meet conformity 99.99966% of the time. That's what it means. So you can see here, there's an example of a red one. The red curve shows that it's meeting the target. However, it's very flat. It means almost how much? Almost 4 sigma is outside the specification limit. 4 standard deviations are outside the specification limit. And number 3 is showing you that majority of it is inside the specification limit. However, it is not meeting the target. There's a consistent more dimension. It's always on the right. So this one usually is because of a specific worker. Maybe they're clamping the micrometers too hard, and then when they machine it, they're always more. They need training, or it means that the machine is not calibrated and the machine is cutting to or doing whatever at the specific target in theory, but when it goes to QC, it's always above. So the best one is the centered one, of course, and the high one. So everything is within 6 standard deviations of the probability is inside the specification limit. This is known as 6 sigma. That's why you will hear many people doing 6 sigma, black belt, green belt, yellow belt. It doesn't matter the amount of belts. It doesn't matter what is happening. You have to understand what it means so that you are capable of engaging and improving. There's no point having 100 certificates when you don't even understand this. Okay, so let's see an example of 6 sigma in real life. Okay, so 6 sigma example in an airline. You have an airline that typically has 1 million flights. Maybe fly, Emirates, Turkish Airlines, whatever it is. They have 1 million flights in a year. If they aspire to get 6 sigma, the flight incidents, which means 3 out of those 1 million flights in a year will be defective, or will be delayed, or there'll be a safety incident. Okay, worst case scenario is a crash. So by reducing this probability, it is very easy to predict if your system is working properly or it's not working properly. So in the case that if you follow the news, the 737 MAX, it crashed. I think there was like 4 or 5 incidents in a span of 2-3 months. Immediately, all the airlines grounded all 737 MAXs. It's because it was going above the predictable limit. It means there was something defective in the plane. That's why it got grounded. Now, there is no need to prove that each one was defective. No, it just means that the production system that those planes moved through in Boeing was not correct. It means defective products were shipped to clients. So the clients grounded all 737 aircraft across the world, and the penalties had to be paid by Boeing themselves. Okay? So we're going to move on to the next concept of quality improvement, which is known as lean manufacturing. Okay, lean manufacturing and flow optimization. Okay, lean manufacturing, just like the name, is comparatively to a human body that has body fat. So excess, unneeded weight that slows down the process. So that's what lean means. So these are lean principles, or they work hand in hand in something called JIT, just-in-time systems, which Toyota helped implement. So this is a very good example of lean. So smooth production flow, reduced lead times, improved quality. That's what it means. So the manufacturing system becomes lean, all waste is eliminated, everything is optimized, So in this case, you can see that we have some key principles. You have the value, so the value stream, flow, pull, and continuous improvement. You can see on the right side, you have the same production system. However, one is considered lean because it's designed in such a way that the product moves through the system very easily. Okay? The top side, you have this haphazard production system that reaches the end and then comes back into this other place and then goes out. But in the second one, you see it's very smooth. It just flows like a production line until the product finishes. Okay. So the term for this continuous improvement, because the ones who invented lean, actually the Japanese. So most of the terminology is coming from Japan. So in this case, Kaizen is known as continuous improvement. Okay. But it's very hard to implement this if the MAIC was not implemented, which is define, measure, analyze, improving, and control. So you must have something that is measurable, that you can analyze and everything, so that you can be able to improve and implement Kaizen. Okay. So there are 3 frameworks for sources of waste in the Japanese culture of lean, which is called Muda, Mura, and Muri. Okay. Muda just means wasteful activity. Like in this case, you see the picture on the right, you see there's a truck that is going to waste all the fuel and the time just on 3 packages. That is wasteful. So the production system or with the delivery system here, it has to be optimized so that these trucks don't come out until they're full. Okay. And then you have the Mura, unevenness. Because of unevenness and inconsistency, you're not capable of being efficient in this case, the delivery system. So you don't have a policy or a strategy in place to not allow things to leave when they're full, in this case, or overburden. So overburden on people or machines, in this case, you're overloading. Overloading causes too many problems, or Muri causes too many problems, because when people are overworked, they burn out. They're not capable of doing their jobs correctly. When machines are overworked, you have something called unpredictable failure. So something that was supposed to be maintained 3 weeks or 4 weeks from now, that has already been planned and put in the production schedule, now just fails all of a sudden. Why? Because the machine has been overloaded this whole time and nobody knows about it. So this is one of the frameworks of optimization. You might think that you're getting out more, but because of overloading and overburdening the machines, what happens is that you will be having unpredictable maintenance needed. And unpredictable maintenance is the worst case scenario, because now you need parts that you didn't order. Maybe the machine is Italian made or the machine is German made, and now there's this part that is broken, and it's a part that needs specialized installation and has to be machined and manufactured and sent by the vendor all the way from Germany. It takes like 4 months. So something that could have just been maintained easily within a few minutes or 1 hour now will take 3 to 4 months. You have a machine that is down, that is critical to the production process. Why? Because you overburned the machine. So this is one of the wastefulness that the lean manufacturing process has. So there is some 7 wastes of lean is such a a coined term called Tim Wood. Okay, so you have transportation, where you have to optimize the transportation. Okay, how the things move inside the facility, how they arrive. Okay, you have to optimize the inventory. You shouldn't have inventory that's not going to be needed. So this comes back to the make to stock. So order to stock, what you need to stock based on the forecast, how it will need. So this is all linked with that. So the next thing is motion, the amount of motion inside the facility. For example, an employee or a worker that is working on a CNC machine has to go back and forth from the inventory 100 times. Why? Because there's a specific tool, there's a holder, there's a cut end mill or whatever it is. Instead, move the inventory close or make a small inventory next to the machine for the worker, so he doesn't have or she doesn't have to waste this time of going back and forth. Okay, another thing is waiting. So waiting is a very big problem, because this is linked with the purchasing department of the company or the procurement department, where the production looks like it's slow, but actually no. When you zoom in and you see why there's delay in production, you see half the time the production is just waiting. This means there is a poor procurement or purchasing method in the supply chain. Why are they waiting? So now as you dig deep as a Lean Six Sigma individual, as you dig deep, you will start realizing why are they waiting. So you'll see, maybe they'll tell you, oh, the procurement order was late, or the vendor delayed. So in this case, it's very easy. You either change the vendor, or as we talked about earlier, you keep a minimum order quantity with the vendor. You tell them, in order for you to do business with us, you need to have X amount of this product within your facility at all times. Otherwise, we'll not do business. So it's very easy. Okay, so waiting. Overproduction. So what another problem of waste is overproduction. You produce parts that they eventually become obsolete, or you produce parts and just keep them in inventory. Okay, this is a principle that is against this, because this is waste of money. So imagine if you're producing things that cost hundreds of thousands or millions even, and just keep them in stock. For what? Because now you just have a million in inventory. Nobody's going to buy it. Maybe the times have changed. There's new electrical vehicles. You produced like diesel vehicles, like billions of them, and just kept them. No. So this is overproduction, overprocessing. Okay, something that is already met the conforming requirements, but you're doing more work than necessary. You're polishing it. You are looking at it, taking pictures. The overprocessing. You don't need this. The product has met conformity. Get it out of the way. Work on the next one. That's what overprocessing means. And the biggest one of the waste is defects. A lot of times, a lot of people don't think defects is a lot of time, because they see the production is going on, people are working. But if you take into account how much defects are there, you will see that maybe 3 or 4 times the production time is taken just because of defects. Things come back returned by the client. Things come back returned by the front workstations. So it delays the whole system. Okay. And this goes into an efficiency. I didn't put it in this presentation, but there is something called OEE. It's called the overall equipment effectiveness. From all these parameters that we talked about, there is an efficiency parameter that you can calculate called OEE. So how much effective you are based on how much time it takes, how much downtime there is, how much waiting time, how much schedule time, but how much actual work time, all these things. So from this, a new term came out called single minute exchange of dies, SMEDs. So there's a principle called single minute exchange of dies. Single minute exchange of dies comes from the manufacturing process of stamping and cutting. So you have a hydraulic press, and you have this die that has to go in. In this case, you can see the picture, the pink one has to go in, has to be bolted, has to be aligned properly, has to be checked if it's going back and forth properly, stamping, forming is doing correctly. Then they start the manufacturing process. So in the past, it used to take 2-3 hours to do this because of the amount of waste. By implementing something called internal and external setup. So what is internal and external? Internal means that the process that is involved in making the part, in installing the die. And external are the process that is not involved. For example, bringing the other die. So that can be done way before they need to change the die. So bringing the die to the station, so this is an activity that doesn't need to be done once the die has stopped. You want to change? No. You have 20 minutes, the tools that are going to need to prepare. So all this can be done. Anything that is outside that can be done before changing the die has to be done. Once the machine stops, the die is removed, the other die is bolted, and the machine continues again. So this also is affected in design. So for example, you have locking pins instead of screws. So if you have precision locking pins, it's very easy. Locking pin, you just press it, pull it out, it's done. But a bolt, you have to screw it in, you have to tighten, you have to check the tolerance if the thickness is correct. So all these things, so even the design affects how fast things change. how fast you can change things. So here's an example. So back in the 1980s, when the first Formula One pit stops, these are called pit stops. As you can see, everything is happening there. The guy on the front there is now putting the wheel, he's hammering it. Another guy comes here, another guy comes this. It used to take maybe half an hour to 20 minutes. And if you see a modern pit stop, it doesn't take even 20 seconds. It doesn't take even 5 seconds. It's like 3 or 4. I think the record is like 4 seconds or 3.2 seconds, something like that. It's because they're following the same principle. What can be done before the vehicle arrives is done. So as you can see here, the wheels are ready. So instead of having 4 or 5 bolts on the wheel, the Formula One people decided just to put 1 bolt, so that it can be removed quickly in and out. You can see the person that is putting the fuel, the person who's putting the fuel is ready, and they're using a high pressure. They're just putting it in, coming out. They don't need to open the cap, put it in, close the cap. It's already designed. So even the design is accommodating to the single minute exchange of dyes. Excuse me. So the combination of these two is Lean Six Sigma. Okay, the combination of these two is Lean Six Sigma, and it was first done by a gentleman called Taiichi Ohno, born in 1912 in the Toyota company. Why Toyota? Because Toyota does it so well that the term has changed from Lean Six Sigma to the Toyota production system. It's so good. Imagine they perfected this. That's why Toyota vehicles are reliable, cheap, and fast to produce. So these 3 terms are coming from years and years of cumulative knowledge and improvements, okay, until they're called the Toyota production system. I apologize. The next thing we're going to talk about, we're done with Lean, is Industry 4.0 or Smart Factory. Okay, so what are smart factories? What is Industry 4.0? Industry 4.0 actually is almost, you can imagine, a layered cyber electronic system that is on top of the mechanical systems in place in the factory, that is then linked with something called Internet of Things, and then displayed in a monitor where you can see the live production. As you can see here, you have the layers. You have the asset, you have the integration, you have communication between the assets. In this case, when they say assets, they mean the machines. So the machines are coupled with electronic sensors, digital twins, whatever it may be, communicate with each other. The information goes to a database, and then there is an AI in this case, or a algorithm or program that decides how to monitor it. And then the functions are given to the human overlord, which is overviewing all this. And all this is called the MES system, or the manufacturing execution system, that is then linked to something called an ERP system, which is the enterprise resource planning system. So the enterprise resource planning system is something that is linked with vendors, sales, all the things. The MES, which is the manufacturing execution system, is just linked with the machines internally, the QC, how everything goes around the factory. Okay, so this is known as, quote, the 4th industrial revolution, the smart factories. Okay, so the most common smart factory system that is available now is SCADA. It's called SCADA, Supervisory Control and Data Acquisition System. It is built by the control engineers deal with a lot of this. So it's built by having a centralized server, and those servers linked to cloud and supervisory computers that are on the devices, which are then linked with PLCs that are in the processing station itself. So you have PLCs that are, there's a board of PLCs that is connected to the sensors, and the sensors can be anything. Can be sensors for electricity current, can be sensors for light, can be sensors for dimension, can be sensors for weight, whatever it may be, that then feed back to the central computer SCADA system then the system decides what to do. For example, you can have a status system in a tank where it reads the level and temperature of the fluid inside. So what happens is that if it reaches a certain level, the sensor inside sends a signal to the PLC system that sends it to the supervisor computer in that local server, that sends to the centralized SCADA computer, and then the computer decides, okay, based on this algorithm to drain, it opens up the drain. Once it goes a certain portion, it closes the drain. For example, or temperature. If it reduces a certain temperature, it does like a thermostat thing and then heats it up again and then cools it down again and tries to maintain that level depending on the program that is available. This is what this has been around for a long time, but there's a new one called SCADA TCP, which is like directly linked with Ethernet. So you have things now known as Internet of Things. So everything is linked with Ethernet with a router. You have servers, you have switches. It's just like connecting a computer. You connect a machine, whether it's a machines that are producing petrol or producing food, whatever it may be. Okay. So this is what I talked about. So now the next step is system integration, where the ERP system, where the employees of the company who are in sales, who are in dealing with the CRM, who are in accounting, finance, human resources, inventory, purchasing, they're all linked with the MES system, which is also dealing with the SPC charts that we talked about. It's dealing with the work orders automatically. It's dealing with everything. So instead of the worker in the production floor calling or requesting the purchasing department that this material has finished, we need to buy more, the system, the MES system, automatically using the status system, it checks the levels, for example, if it's a weight, it automatically communicates with the ERP system, which is the purchasing module that communicates and issues automated purchase orders to the already approved vendors. You see how these things can now be automated, and this is done in real time. So end-to-end information from the shop floor to the client, from the vendor, everything is linked in one system. The client, the moment the production QC MES system approves it automatically, it's connected to the ERP sales system, sends an email to the client, their product is ready. Okay. Then we move on to Internet of Things. So Internet of Things, all that is not possible if you don't have Internet of Things, smart factory. You don't have these sensors that are compatible with each other. So nowadays, everything just uses Wi-Fi and all these things. And then it collects consistent data. It doesn't just take snapshots anymore. It collects maybe in a day gigabytes of data continuously from everywhere. So this is called big data analytics, if you've ever heard of it. This big data now, from the motion of the machines to the tolerances, temperature, all kinds of parameters, the electricity that's coming in, everything, is jumbled up in this database as raw data using the Internet of Things principle, because everything now is connected to one centralized system that then is displayed and converted and translated to a UI that the end user or the owner of the factory in this case, or the plant manager can see on their phone. How many invoices have come out, how many products came out, how many things have gone missing, how much money was spent, everything is linked to one thing. Different dashboards for different employees and managers. Okay, so this is a picture of a smart factory model. You have elastic talent, management, cyber, supply chain, productive reality, almost a digital twin of the factory in a computer. Okay, that's the whole point. So a factory can be managed from anywhere from a computer. So now we move on to AI and machine learning. So Where does all these things come in? Instead of a human now behind it, you have an AI that is behind it that is making the decision for you. Okay. Excuse me, I need to get a little bit of water. Just okay. Apologies. So, so the AI will now have a predictive maintenance and optimization schedule, let's say, based on the data that is arriving from the IoT items. Okay, and it can detect or even predict anomalies and failures better than humans based on which AI model is trained. So we're talking about reaching a stage that they are no longer human workers. They are no longer human in the facility because the AI robots are directly communicating with the general AI that is there. You have no human interference. This is where we're going. Okay, so this is where the world is heading, where everything is decided by the AI. You have multiple AIs. Okay, and this is a reality. This is no longer fiction, as you can see here. There is a picture you can see as of 2024, or this is 2025. As of 2025, you already have humanoid robots ready. They might not be ready for every industry, but we're getting there. Okay, so you reach a point, there'll be no longer welders, no painting, no workers that are moving this item here and there. These are just the humanoid robots. Okay, they are more already. These things are done automated, like in Amazon. Amazon already has these small robots that are carrying the boxes to the warehouse and everything. Some things that were done with humans in the past now no longer. In Amazon, humans are just interfering with the process. Okay. So where does this put you? Where does this put us? Okay. Contrary to belief that AI will take all the jobs, it's not true. Okay. AI will not take all the jobs. AI will take maybe 80 to 90% of the low-skilled human jobs. So due to the 80-20 principle here, what we talk about, the 80% of the work is done by 20% of the people, only the best will be hired. Only the best will be working, because there will be no point of having average. Instead of having 100 software developers, you can have 2 good developers or 1 very good developer partnered up with a main AI that will be able to develop with the same speed or even better than the 10 or 20 developers that were hired before. Only the best will be selected. They'll be working closely with AI and then communicating with other AIs. So you will have specialized AIs, AIs that speak to clients, AIs that do specific things, communicate with vendors, AI that can pick up phone calls. Somebody called your company, you have an AI picking it up. So who will be managing all this? You'll have human, of course, but only the best. So keep up that high GPA as much as you can, and always improve yourself, because we're heading in a world that being average is not enough. Being better is not enough. We're reaching a world that only the best. Okay, so don't let AI do your thinking. Improve yourself. Don't outsource your thinking. Do it yourself. Understand the concepts properly. Learn how to use AI as a tool, beneficiary, and then you will be amongst the best. Okay, more jobs will be created, such as jobs for maintaining the machines, jobs for programming, jobs for prompting the AIs, so many jobs, making the SCADA system jobs, SCADA system setting up, all these things, process improvement. So the grunt work of humanity has already been taken by AI. So all the jobs that will be there will be the important ones where you actually have to think. Anything that can be done by AI will be done by AI eventually, regardless of what happens. Okay, as the world progresses, we're moving to a stage that if you don't use AI as a tool, you will be out of the job. Okay, so this is the end of the presentation, guys. Thank you. If you have any questions, now we can start. Okay.
Omar, thank you very much for your
Welcome.
presentation. It was very informative to me. As you know, my field is energy, but I learned a lot today, and it was a
Great.
very smooth, nice presentation. Thank you very much.
You're welcome. So let's start taking questions.
Omar, thank you very much. Actually, you made a very good revision for me. I used to teach this course to graduate students, and it's amazing that how you have put the whole topics into us, how you have like introduced so many concepts.
I'm
I
glad.
remember for this Muda, Mura, and Muri, I just have one lecture on Muda, Mura, and Muri, and you have covered almost all the fundamentals that is required for undergraduate students in a very, very concise, accurate, and still yet elaborate way. It's amazing. Excellent. Thank you so much. Thank you so much.
I'm glad.
Okay. So I believe most students, because of this new year, they are not available here. But still,
Yeah.
I will ask some questions. But if any student has any question, my friends, please raise your hand. Not yet. Okay. So do you have any question, my friends? Anyone? So Umar, I will.
Not for me, thank you.
Okay. So I will ask some questions, which generally come from students. I will want your insight on that. First of all, give your insight on use of AI for students. Okay. Although you just mentioned about the use of AI, but in research, in your professional studies, give a brief insight, although we can have a separate seminar on that as well, how to use AI in your work environment, in your job, in your research. But you as a professional, how do you manage with this? How do you use artificial intelligence tools in analysis and technical report writing? And how much do you rely on them? And how much do you believe the outcome of that? Just a quick answer. Thank you very much.
You're welcome. Okay, so the question is the use of AI. Okay, this question comes a lot. One thing I'd like to compare the AI to is like holding a sword without a handle. Okay, AI is a very good tool, but it's also very damaging, especially to oneself without knowing. Okay, we see a lot of this example in real world. You have a staircase and you have an escalator. Staircase, you have one or two guys going. Everyone is packed in the escalator. If you ask each one of these gentlemen or ladies, is the escalator or the stairs healthier on your body? Everyone will tell you the same thing. The stairs is healthier. Yet everyone is taking the path of least resistance, going with the escalator up. So it's the same thing with AI. Unfortunately, I have to say this. A lot of graduates that have been coming out with AI have outsourced their thinking to AI. So that's like any muscle. If you don't use it, you will lose it. Okay. So using AI is not a problem. using AI as a method to outsource your full thinking is a very big issue, because once or twice will not affect you. Just like if you go to the gym, the muscles will not grow once or twice. You don't lose all your muscles by leaving the gym in one day. You lose muscles after leaving it and skipping it for months or weeks. It's the same thing with AI. One time, two times is fine. But as students and new engineers outsource completely their thinking to AI, now it starts becoming a problem, because they don't know anything. They not only did not learn it, they outsourced their full thinking to the AI, and they don't know if the AI is right or not. It's very hard to know if the AI is right or not if you don't know what is right, if you didn't practice, if you don't have the knowledge, because from the university days, from the beginning, you've been outsourcing. So AI is such a wonderful tool. You can outsource heavy work. Like, for example, you can have AI help you find where to get the ideas. Which books can you read to summarize something? But to write a complete report, is completely, eventually people will know, okay, that it's AI that wrote it, and there is no substance to it, because somebody has used AI for so long, they no longer know how to even do the thing that they are supposed to be doing. So these jobs that require AI eventually will be removed, because AI can do it. So if you are amongst the people that is just outsourcing your thinking to AI, and you're getting the job done because of AI, then my friend, trust me, with time, you will be just like that AI, you'll be replaced. A new AI will come there, and the company will use the AI directly. I hope I answered your question. I can't hear you.
Asim Hoca, yeah.
Yes, indeed, indeed. Thank you, Umar. And I always like use this terminology in different way. I said it's GIGO, garbage in, garbage out. So if you are not putting the right query, not the right thought, you're not asking the right questions in the right way, and then using it, the tools and the appropriate tools, and the feedback that you're getting, you're not verifying it, then it's absolutely wastage of time. Okay. Anyone else? Any questions, my friends? Okay, I have a few more. Umar, again, I'm very grateful to you for your valuable time and everything. Umar, based on your experience up till now, I think you graduated in 2017, if I remember rightly. It's been now almost we are
9
entering
years.
into 2026. So it's been approximately 9 years now that you are a graduate. So you have almost spent a decade in the field.
Yeah.
Part of it you have worked as a quality assurance in standardization and Six Sigma, and now you are you're an entrepreneur. You have your own company.
Yeah.
Okay, which is
Yeah.
great to hear. So, what advice do you give to engineers of today? Which career path they should follow? Which skills they should learn as they are getting out into the job market, or before they get out into the job market, which skills they should work on based on your decade of experience?
Okay, so it's a very tough question, but I can say based on in my opinion. I think again, this is an opinion. It doesn't mean it's true, but based on my opinion, certain skills have to be learned by students before entering the field. Okay, so such as in this case, if you're going to be doing automation, okay, automation is something that's pretty good to learn. Learning how to use these systems, SCADA systems, and all these things. It's very, very good if you're entering the manufacturing field, because now, as I said, most industries are transitioning to 4.0. So a standard mechanical engineer that doesn't have deep ingrained programming skills will be very tough to make it. Okay. So skills, increasing your skill set. Okay, papers are not everything, but increasing your skill set, yeah, it's very good. Getting like industry specific certificates. So for example, as this one, Lean Six Sigma, you can get, if you want to be project management, that is PMP. Getting licensed specifically as a professional engineer in the country you're operating in is also very important to do, because with time, eventually it becomes, not only does it become needed, it starts becoming mandatory. Okay, about 6 years ago, not even 7, I'll say 3 years ago, being a professional engineer was not mandatory. Okay, now it is. So industry specific certificates is good. Again, depending on how the person wants to proceed with their career. If there is a career specific questions, I will answer. It's fine.
Like someone who wants to, let's say, work in automotive, okay? Because many engineers, when they graduate, they believe that from day one, they're going to be designers. This is something which gets stuck in their minds, that they will start as system engineers and designers. So please, like, give your insight into that. What, like, of course, they can, everyone, like, not everyone, but they, in a way, everyone, like those who try, work hard, can become designers and system engineers. But what's the right way forward? Where they should start? And then they can, like, in a period of 3 to 4 to 5 years, or maybe 10 years, they can reach that level of becoming a designer of something.
Okay, so actually that question, that same mindset I had when I started. I was looking for design engineering jobs. If you see mechanical design engineer, you will see that they need like 5-6 years of experience in design. So with that said, I was really good at designing. However, really good at drafting, I'll be specific, but designing parameters, I was still fresh. So I actually, my first job, I didn't even look for the word engineer. I literally was looking for a job for draftsman. So I found a job as a draftsman. So I was just drafting. But this is how I entered the field of design. Okay. And then as I progressed, I became a junior designer, and then I became a mechanical design engineer, and then I became a lead mechanical engineer, and then an engineering manager, and then a manufacturing and engineering manager in the field of manufacturing. Once I reached that level, I saw that there are better opportunities when, not better, I'll say there is more high-paying opportunities more in the field of engineering cross with management and operations. So having more responsibility. Although they were more, if you specialize more in like master's, PhD, then yes, there is more very good opportunities in research for these things. So there's also that path. So there is a path of becoming, let's say, more into engineering management or more into deep technical. So this is I'll say these are the main career paths that I saw in my career.
Thank you, Umar. Umar, one more question. Actually, I have a lot of questions. The students, they keep asking me. Some of them were supposed to be here. They are not here today. So I'm taking the liberty of asking those questions on their behalf. We have a student, he is not here. He asked me this question, and I specifically told him that we are going to have a webinar next week. Please join in and ask this question. You will get a better answer than what I give. Because, I've been out of industry for about, the same time. I've been out of industry for more than 10 years now. So I can give answers, but not the latest answers. Like I told you before as well, that when I was in industry, we were doing AS 9100 revision B, whereas I believe you have worked on revision C. Yeah. So things have changed, things move on. In 10 years, it's a different world altogether. So there was a student, he asked me, because in our courses, in all our courses and in undergraduate education, we focus too much on report writing. presentation, report writing. So some students are of this opinion that no, we don't need this. Why? Because we should only focus on the technical aspect. We shouldn't be giving this much value to like technical report writing and documentation. So how much, in your opinion, still as of today, documentation is important in the field as a profession?
Documentation is everything. We have a saying in our industry. We say, if it wasn't documented, it didn't happen. So if it wasn't documented, it didn't happen. So if, for example, you're receiving an item that was machined and then heat treated and then painted, and then they give you the certificate of conformity. This actually happened. So they give you a certificate of conformity that it shows you with the work orders, all the steps that happen. And then there was no work order for heat treatment. And then I asked them, like, okay, you vendor, why is there no work order for it? No, we did it. No, really, we did it. It happened. They just forgot to record it. And that's when I remember. So if it wasn't documented, it never happened. So it's really important. Report writing, documentation is everything in the industry. There is the difference between workshop and a factory high-end 4.0 is documentation. However, nowadays, majority, I'll say the heavy grunt work of the collecting of the dimension and the data and making it all, that part has been handled by AI and big data analytics, and the documentation of the raw data has been done like that. But making the final documentation that is presentable to stakeholders, it's very hard. You as the engineer, you understand. You see the data coming from a SCADA system. It's like 3,000 pages, 4,000 pages. I mean, yeah, documentation, but are you going to truly present 3,000, 4,000 pages to somebody who has never seen a calculus equation? No. So you as the engineer, you have to be able to present this data in a more sophisticated way to other engineers. Okay, you have engineers in other companies, your client company. They're not interested in the 4,000 sheets of data. They're interested in the key things. So by taking this and using AI and big data analytics strategies, convert it to visualized data and taking key images and making your report professional with a, with list of figures, list of equations, list of how that data arrived, and making those documents, making those reports is almost a make it or break it with our clients, because that report determines the perception of professionality of your company or that engineer. So if you are haphazardly making a document using AI or whatever it may be, and you have all these small mistakes, you don't notice it, nobody tells you. But for example, me, when I'm reviewing work for other engineers, I'm a principal engineer, and when I'm reviewing work of other engineers, I don't go and tell them, why is this font smaller? Why is it not aligned? I don't tell them. But when I receive a report from an engineer who has actually taken the effort and done his alignment correctly, fonts and whatever it may be, and professional and everything, automatically at the back of my head, I already know this is a better engineer. I already know that if there's a promotion, it's this guy. It's not this other guy. But I don't tell them, because that engineer, the one who gave me a report with mistakes, is good enough, is average. But in roles of leadership, in roles of higher responsibility, you don't need average. You need the best. So how is that determined? It's determined by the level of your work. You're good at making reports, great. Can you imagine? I receive reports from engineers that the page number is written manually. I mean, AI does that, but okay, it's written manually. I told him, edit this, add this, and then page number 5 was like 10 times. So it's, I mean, I have to tell them, like, you have 4 years of experience, 5 years of experience. Why is page 5 times? Why is page 5 6 times? Oh, I forgot to edit it. Why edit it? There is a tool for it. There is a standard way of doing it. I mean, it's very easy to cut bread with a spoon, but if you have a knife with you, why not use the knife? No, you have a hammer and your fist. You can still fist in a nail, but if you have a hammer, why not use the hammer correctly? You know, so this is the thing. You have to understand how the tools that you have work. You have to be professional in your work. You have to make sure the work that is given is in a perfect state, because with engineering, especially in consultation, the clients that are receiving your work, they know you are the consultant. So when the client corrects the consultant, why did I pay you? Like, why did I pay this consultant when I'm correcting his work? So that's how it is. So the work has to be perfect, error-free, completely professional, aligned, just the way you did it in your capstone project. So if you, professors, are accepting errors and not automated list of figures, and then that's carried forward to the engineering departments across the world, and then those engineers become managers, and then they accept lower level skilled engineering, and then you have this feedback loop of less qualified engineers proving even lesser qualified engineering works.
Thank you very much, Umar. So, although I don't want to make it an EMU promotion or Department of Mechanical Engineering promotion, but how well did the capstone documentation, report writing, and all these activities helped you with this kind of skills?
You might think I'm exaggerating, but I would probably not be CEO, because the level of report that was submitted to my managers before is what highlighted my skill set. Yes, the work was done correctly, but that one showed the level of professionalism. I was so reliable, to the point that the managers and the supervisors that were assigning me tasks, if they wanted something to be done correctly the first time, they will hunt me down amongst all the engineers that are there, and they would request me to do this. Sometimes I would be called in other departments to do these reports, to make it for them. Sometimes they will send like, please fix this for me. And I'll just, out of my scope of work, but I fix it and I give it and I do everything automated. And because many engineers don't know this. Many engineers who come out from other universities don't know about these things, and they don't care about these things. And it's not very, for them, it's like, okay, but the information inside is right. Yeah, the information inside is right. But giving that report to a client, the client can decide if to give you another order or not. Giving that report to a manager, the manager can decide to give you a promotion or not. So really substantially built up to the position until I'm a CEO, because I am able to correct engineers' works. So the team, most of the time, I hire not fresh graduates, but sometimes fresh graduates, sometimes 1 to 2 years experience, and I correct them. But the engineers that were there before, that are now the lead engineers managing the smaller engineers, before the report reaches to me, they tell them this, the CEO will not approve of this. Why? Because you see, this font here is 14 and here it's 12. This he will not approve. And it's true. So the engineers have, the leads in my company have created filter on how to get perfect job, because it's their next on the line, the leads. Because I'll say, how did you sign this? How did this engineer of 2 weeks and you are here for 4 years, how do you sign this? How do you do not see all this? You do not see that here, this is AI. It says, do you need me to do this? Did you not see this AI line here? How are we going to deliver this? So as I progress and tell these leads like that, and I reprimand them, I said, if you keep this up, you will no longer be a lead. I will find other leads who will actually be able to do the job. So they take the job very seriously about reading reports and making sure the fonts are aligned and everything perfectly, because it's easier to find, it's easier for somebody to trust your organization, your skills, when you take care of the little things. If you don't take care of the little things, you will not care about the big things. So if you care about the little things, people have this form of like trust. It's the same deal with like iPhone, because iPhone and Apple, they take care of even the Philips standardized across all their products. They take care of the little things. So that's why they are where they are today. They take care of the little things, and the big things automatically are correct. It's not possible to miss a big thing when you're worried even all the little things.
Thank you, Umar. Thank you so much. Murad Hoja, you have anything to say, please?
No, I would like to thank again for this
You're welcome, Professor.
very nice presentation, Omar, and the career guidelines and your experience. And it's good to see that
It's
our
good to see
work-
your product.
Yes, this is what precisely I was about to say. Particularly, Kasim Hoja helped a lot putting the capstone projects to a standards and which produce such a good product. You are our
Yes.
product. So
Yeah.
thank you very much again, and
You're
hopefully we invite you here next time to give us a face-to-face presentation.
Oh.
Thank you very much.
I would just like to add one thing. Like a diamond is a diamond. We just cut it. Okay. So if a diamond is a diamond, okay, we cannot make a diamond. Okay. So we are the ones who just refine it. We just cut it. Okay.
Refine it.
So we don't make diamonds. You are the
True.
diamonds. So we just refine things. We try to add value to it, but you are automatically, originally, you guys are the ones who are, and it's your own hard work and labor that what you have achieved. Umar, you have a lot of alumni in Saudi Arabia as well, I believe, from EMU. So why don't you make how to say, what's the right word for it? I'm not getting the word for it, like a committee or like a union of them. So you can all be in contact with each other, and we can have more sessions like this, not like a seminar or something, just like a discussion with all of them. And you can be because you are already very active with us, you are our advisory board member as well. So it will be very good that we can have like a union of all the alumni from EMU in Saudi Arabia. And I believe you're already in contact with some of them through your work.
Yeah.
So it would be very nice that if you can arrange something and we can have a discussion and meet and greet online, of course, with all of them. If you can arrange something like this in the future, that would be very nice for us and the students as well. Okay, ladies and gentlemen, do you have any questions? Yalda, daughter, Zainab, any questions? Siddharth, Elia, anything you want to ask, my dears? Awab is the one who was here even before us. Awab, do you have anything you want to ask?
I would like to thank Mr. Omar for this seminar, and it was like a refreshment for. Can you hear me well?
Yes, we can hear you, Mr. Omar.
Yes, it was a good seminar, Mr. Omar. Thank you again.
You're welcome.
Thank you all for joining. Mark.
Yes.
Do you have any questions, my dear?
No, sir.
Siddharth, Elia, anything? Yes, Siddharth, please go ahead. We just have 5 more minutes, so please keep it short. Thank you very much.
Hello, Mr. Omar. Thanks
Hello,
for educating us today. I would like to ask you what's your opinion in improving agriculture by AI integrated tools such as drones or other kind of overlays. Like you are currently working for OnAlt Group, which are producing chemicals or construction, I guess.
No, I
No.
work in a consultation firm. But
Sedat,
I can answer your
think-
question.
Yeah, go on, please. You confuse him with our other alumni, Hamza Sajid. But Mr. Omar will obviously will answer your question. Please, Omar,
What
go ahead.
What is your
All right,
question
then,
specifically?
let me say, as a CEO, like, you are much morally skillful than any regular people with meetings and stuff.
Okay.
How would you suggest us to present ourselves to the bigger companies so we can find funds? Even if our project is mainly not ready yet, like incomplete, but we have an idea and we would like to share it with them.
Let me put the question in. Umar, they are looking for sponsors for their project.
Okay, so he had two questions. The first one was regarding agriculture and AI. The second one is regarding sponsorship of your project.
Sponsorship
for project.
For the project, yeah.
Okay, getting funding for projects, it has to be significant to the company. So if it's something that is going to add value to the company, it will be, they'll definitely sponsor you. For example, if you are, I did this one time, if you're doing your project in improving the speeds of a CNC machine, you go to a CNC machine company, for example, in my case, our Dener Makina in Turkey, they had their head was very heavy, so it reduced the acceleration speed. The acceleration was very slow, and then stopping it was even harder, and it used to burn out the motors. So some project for us was reducing the weight of the head and finding the problem, optimizing it. It was value added to the company, so they were ready and willing to sponsor. Because for them to do that improvement, they would actually need to hire very skilled engineers or a consultant to do it, which will cost them millions or sometimes hundreds of thousands. So why do that when you can actually fund students who will do it for you and give you exceptional results? So it's just value added to the company. Anything that will add value to a company. What project are you doing exactly so that I can have an idea, Mr. Sedat?
Actually, what you ever said is very specific, like making maintenance on a current machine. We are not doing that. We are starting from scratch. We were actually, my friends were designing a drone which will be guided via AI and will stand as a shepherd drone, let's say. Like, it will do what a real life shepherd does in Cyprus, in big fields. It will circle around the sheep and guide them to the point.
Okay, that's a pretty good idea. One thing you should ask yourself, if that thing already exists at a mass production rate where the shepherds can just buy it directly. That's one thing you should ask yourself. You should ask yourself, the way you are designing it and manufacturing it, is it going to be sustainable? What is the future improvements that you can do that? And you have to present, we can call it a pitch deck to the shepherd, like how is he going to save money? Because everything is driven by money. So how is he going to save money by doing that? For example, your drone, you need a funding of $5,000, $6,000, $10,000, let's say. And then you show him over the years, for example, 10 years, 5 years, each year he'll be saving 200,000, 300,000 by implementing this, by funding this project. So it's a no-brainer for the shepherd to give you the funding. If you just created value for them, but you need a pitch deck. You need to tell them, you need to show them, like, we're doing research on this. If it's successful, which we think it was going to be successful, you will cut down costs by this much here. You'll be able to recognize this. You have a proof of concept, that's good. If you have a proof of concept, that's even better. It will be able to do this and that and all that. Okay? He funds you, you do it, one more thing. Once you get out, I give you advice to patent it if it's not patented yet, because it means somebody can just take that idea, mass produce it, and take your credit. So try to, if it's a good idea, if it's you've seen results, patent it. Patenting is not cheap. So perhaps you will need to create a company. Once you create a company, you should partner with an investor or something like this, and explain this to them what your product is. Do a startup, give them shares, whatever it is. They will fund you for the patenting, for the prototyping, for whatever it may be. And that's how you grow your product, whatever this product is that you're enthusiastic about. If it exists, if it doesn't exist and it's going to add value, tremendous value, I mean, why not?
Yes, sir. We were just thinking about staying in Cyprus with our friends and starting that little own company. Obviously, we are not sure of our proof of concept because the only way we can see is make it done. For now, we already spent $5,000 budget from my friend's sponsors. Like they funded us for the components, but as the problems occurred, trials flight are gone, the expenses are increasing.
Who is amongst your team? Who is amongst your team? What disciplines?
Excuse me?
Which disciplines how many in the team members? Are you all mechanical engineers?
We have a mechatronics engineer and the remaining are mechanical engineers. We are currently recently we hired an software engineer as well, but he just quit. We are looking for a new one for AI integration and stuff, or we are just learning Python and YOLO right now. Actually, we are trying to.
Okay, that's good. If you can partner up even with another university, or if EMU, I don't know if EMU offers even aerospace engineering, I think they will also be very beneficial, because some things you as a mechanical engineer, your brain is trying to crack it within the knowledge that you have, but then all these things already exist that an aerospace engineer knows about. For example, the aerodynamics, the efficiency, the noise, whatever it may be. For example, you're designing the blade in a certain way. If you have an aerospace engineer in your field, in your team, they will tell you, okay, this is not logical. This is the standard industry, whatever it may be. Get somebody in your team, maybe I don't know, in economics or something, to help you with the funding and the budgeting and all these things. Okay. It's also very easy to find it. There are many research grants that are with agriculture. Okay, that if you can even progress half or a portion of it in your capstone, if you're planning to do further studies in your masters, you can do it and get a grant for it. And many universities, they offer this for research on agricultural improvement. There is funds dedicated for these things already in place. You just have to do an application. So there are many ways you can get funding for this. You can get you can get into an agreement with another drone and AI company, but this one is usually very, very hostile, because you will have to like give up the rights to your discovery, so it's not patentable. So you can get into an agreement with a AI drone company, contact them, tell them I'm working on this research, blah blah blah. We need funding this much based on this plan, and whatever research we do, it will be public, or we can submit it to you, or we can share. Usually, no company will want to share because they're already established. Why should they share with a student? So there are many ways, again, to get funding. It just matters which path you want to take. Okay. I started this company not with my funds. I found the same way, just like a capstone project. Found another investor, gave him a pitch deck. He agreed. We started the company. There's another company did the same thing. So multiple companies, same way. Okay.
Yeah, just as you said, like Cyprus is a little field right now. It's expanding, and we thought there wouldn't be any competitors, and there wasn't such an idea as we researched for. Currently, only it was an academic research from Sweden, as I remember. So we will be trying to improve that one. And as you said, yeah, it might be nice to contact with some agriculture companies. But again, as I said, like we are at the beginning, at the early stages.
Yeah, it's fine. This goes under, all companies have budgets. This goes under the budget of R&D. So they will just budget it out for you. It's not a big deal. Big companies already have budgets for these things. So something like 5,000, 6,000 will not be a big deal for them to tell you, okay, it doesn't have to be in Cyprus. I mean, you can do it in Cyprus, but the company doesn't have to be in Cyprus. You can be even, like, let's say, close by Turkey, like this is very easy.
That's correct, sir. Maybe I can do some additional research against my team members. At least it will be useful for me.
Okay.
It's okay. You got your answer?
Yes, Professor. Thank you so much.
You are most welcome. Elia, you were raising hand, although our time is up.
No, it's fine. I have time.
You are so gracious. Yes, Elia.
Hocam, actually, he kind of answered it. First of all, thank you for your presentation. It was very useful. I want to ask, I mean, when we want to talk with a company, for now, I mean, after graduation, for me, I don't have the confidence to do that. I mean, they don't count us. I mean, I think okay, somebody just opened the door. I have an idea. Why should they answer me or talking with me and discuss about their things to me? This is the question that I want to ask. That how we can talk with companies or sharing ideas with other.
Or sharing ideas or getting a job. Which one are you talking about?
Actually, sharing ideas to not getting a job. I mean, to kind of same as Sadat question, to find a sponsorship or maybe okay, I have a idea to improve what any section in their job anywhere. How we can discuss it with them.
Okay, so what project do you have in mind?
Nothing yet. I mean, generally, I'm asking that how can I?
Let me give you a hypothetical scenario. Okay. I don't know if there are air conditioning companies in Cyprus. I don't know. For example, you have a company called Carrier. They wrote their efficiency is like 60 or 70, 60, 65% efficiency. Let's say you're in the HVAC business. You can do a pitch deck. Go to these people. They have an R&D department. You can tell them, I will work for you as an intern, whatever it may be, and I will be working on this research. For example, tell them the target is to improve the efficiency from this to this, from 60 to 70. The company will not tell you no. It will be illogical for them to tell you no, because for them it's free money. Okay, for them it's free. Right now, for example, right now, if I have a company, let's say, for example, I'm doing poultry. If I had a company with poultry business, and as students from an agricultural university come to me and tell me, our project is to map out and find inefficiencies, but we need like $4,000. I say, fine. Okay, we'll get into an agreement. Whatever findings you find, you'll give me. It's mine. We get into an agreement, they get their funding based on milestones. Again, it all comes down to one statement: adding value added. If you add value to the company, in the long run, they are fine. They have no issue. If you have for example, the sanitation system, for example, in Cyprus, it was designed in the 1980s or 1960s. It's still on calc. It's still on hard paper A0 drawings. If you approach the sanitation authority in North Cyprus to tell them, I have a project to modernize it and find inefficiencies and all these things, they will even fund you. They'll tell you, okay, so you will do what I will make it into, for example, I will use Revit, I will do the analysis, the water analysis, I will find where the problems are, I'll find this, I'll find that, anything, whatever it may be. You, as long as you're adding value, you will always reach the right person. Okay?
Okay, thank you so much.
You're welcome.
Yes, my dears. Any more questions? Murad Hoja,
No, thank you.
can we call it a day now?
Oh.
It's been a long
Yeah,
day
yeah.
for us as well as for Umar. We are so grateful, Umar, for your time and for your effort. I really enjoyed the lecture. Really, it was great. And I'm gonna put it on our department YouTube, so our other students can also watch it when it's available to them. When they are free, of course, they can access it. Thank you very much, Umar. I'm going to stop the recording, and if you have to say anything, please go ahead.
That's it. Thank you.
Okay, let me
Thank
stop the
you for
recording
having me
first.
here.
It's our player, always our player, always our
Thank
player.
you very much again.
Thank you, Umar. Have a good evening.
Thank you.